History. Thomas Young was presumably the person who first used and invented the name index of refraction in 1807. At the same time, he changed this value of refractive power into a single number, instead of the traditional ratio of two numbers. The ratio had the disadvantage of different appearances. Newton, who called it the proportion of the signs of incidence and refraction, wrote it as a ratio of two numbers, like 529 to 396. Hawksby, who called it the ratio of refraction, wrote it as a ratio with a fixed numerator, like 10,000 to 7,451.9. Hutton wrote it as a ratio with a fixed denominator, like 1.3358 to 1. Young did not use a symbol for the index of refraction in 1807. In the next years, others started using different symbols, n, m, and micro. The symbol n gradually prevailed. Typical values. For visible light, most transparent media have refractive indices between 1 and 2. A few examples are given in the adjacent table. These values are measured at the yellow ℏ line of sodium, with a wavelength of 589 nanometers, as is conventionally done. Gases at atmospheric pressure have refractive indices close to 1 because of their low density. Almost all solids and liquids have refractive indices above 1.3, with aerogel as a clear exception. Aerogel is a very low-density solid that can be produced with refractive index in the range from 1.002 to 1.265. Moissanite lies at the other end of the range, with a refractive index as high as 2.65. Most plastics have refractive indices in the range from 1.3 to 1.7, but some high refractive index polymers can have values as high as 1.76. For infrared light, refractive indices can be considerably higher. Germanium is transparent in the wavelength region from 2 to 14 micrometers and has a refractive index of about 4, making it an important material for infrared optics. Refractive index below unity. According to the theory of relativity, no information can travel faster than the speed of light in vacuum, but this does not mean that the refractive index cannot be lower than 1. The refractive index measures the phase velocity of light, which does not carry information. The phase velocity is the speed at which the crests of the wave move and can be faster than the speed of light in vacuum, and thereby give a refractive index below 1. This can occur close to resonance frequencies for absorbing media in plasmas, and for X-rays. In the X-ray regime, the refractive indices are lower than but very close to 1. As an example, water has a refractive index of 6,999,999,999,740,000,000 spadesuit 0.9999994 equals 1 minus 6,993,260,000,000 spadesuit 2.6 times 10 minus 7 for X-ray radiation at a photon energy of 6,995,480,650,2,946,099,999 spadesuit 30 keV. Negative refractive index. Recent research has also demonstrated the existence of materials with a negative refractive index, which can occur if permittivity and permeability have simultaneous negative values. This can be achieved with periodically constructed metamaterials. The resulting negative refraction offers the possibility of the superlens and other exotic phenomena. Microscopic explanation. At the microscale, an electromagnetic wave's phase velocity is slowed in a material because the electric field creates a disturbance in the charges of each atom. proportional to the electric susceptibility of the medium. As the electromagnetic fields oscillate in the wave, the charges in the material will be shaken back and forth at the same frequency. The charges thus radiate their own electromagnetic wave that is at the same frequency, but usually with a phase delay, as the charges may move out of phase with the force driving them. The light wave traveling in the medium is the microscopic superposition of all such contributions in the material, the original wave plus the waves radiated by all the moving charges. This wave is typically a wave with the same frequency but shorter wavelength than the original, leading to a slowing of the wave's phase velocity. Most of the radiation from oscillating material charges will modify the incoming wave, changing its velocity. However, some net energy will be radiated in other directions or even at other frequencies, depending on the relative phase of the original driving wave and the waves radiated by the charge motion. There are several possibilities. If the electrons emit a light wave which is 90 degrees out of phase with the light wave shaking them, it will cause the total light wave to travel slower. This is the normal refraction of transparent materials like glass or water, and corresponds to a refractive index which is real and greater than 1. If the electrons emit a light wave which is 270 degrees out of phase with the light wave shaking them, it will cause the total light wave to travel faster. This is called anomalous refraction, and is observed close to absorption lines with X-rays, and in some microwave systems. It corresponds to a refractive index less than 1. If the response is sufficiently strong and out of phase, the result is a negative refractive index. If the electrons emit a light wave which is 180 degrees out of phase with the light wave shaking them, it will destructively interfere with the original light to reduce the total light intensity. This is light absorption in opaque materials and corresponds to an imaginary refractive index. If the electrons emit a light wave which is in phase with the light wave shaking them, it will amplify the light wave. This is rare, but occurs in lasers due to stimulated emission. It corresponds to an imaginary index of refraction, with the opposite sign to that of absorption. For most materials at visible light frequencies, the phase is somewhere between 90 degrees and 180 degrees, corresponding to a combination of both refraction and absorption. Non-scalar, non-linear, or non-homogeneous refraction. So far, we have assumed that refraction is given by linear equations involving a spatially constant, scalar refractive index. These assumptions can break down in different ways, to be described in the following subsections. Birefringence. In some materials, the refractive index depends on the polarization and propagation direction of the light. This is called birefringence or optical anisotropy. In the simplest form, uniaxial birefringence, there is only one special direction in the material. This axis is known as the optical axis of the material. Light with linear polarization perpendicular to this axis will experience an ordinary refractive index No, while light polarized in parallel will experience an extraordinary refractive index Ni. The birefringence of the material is the difference between these indices of refraction, delta n equals Ni minus No. Light propagating in the direction of the optical axis will not be affected by the birefringence, since the refractive index will be No independent. If polarization, for other propagation directions, the light will split into two linearly polarized beams. For light traveling perpendicularly to the optical axis, the beams will have the same direction. This can be used to change the polarization direction of linearly polarized light to convert between linear, circular and elliptical polarizations with waveplates. Many crystals are naturally birefringent, but isotropic materials such as plastics and glass can also often be made birefringent by introducing a preferred direction through e.g., an external force or electric field. This can be utilized in the determination of stresses in structures using photoelasticity. The birefringent material is then placed between crossed polarizers. A change in birefringence will alter the polarization and thereby the fraction of light that is transmitted through the second polarizer. In the more general case of trirefringent materials described by the field of crystal optics, the dielectric constant is a rank 2 tensor. In this case, the propagation of light cannot simply be described by refractive indices except for polarizations along principal axes. Nonlinearity. The strong electric field of high-intensity light may cause a medium's refractive index to vary as the light passes through it, giving rise to nonlinear optics. If the index varies quadratically with the field, it is called the optical Kerr effect and causes phenomena such as self-focusing and self-phase modulation. If the index varies linearly with the field, it is known as the Pockels effect. Inhomogeneity. If the refractive index of a medium is not constant but varies gradually with position, the material is known as a gradient index. A green medium and is described by gradient index optics. Light traveling through such a medium can be bent or focused, and this effect can be exploited to produce lenses, some optical fibers and other devices. Introducing green elements in the design of an optical system can greatly simplify the system, reducing the number of elements by as much as a third while maintaining overall performance. The crystalline lens of the human eye is an example of a green lens with a refractive index varying from about 1.406 in the inner core to approximately 1.386 at the less dense cortex. Some common mirages are caused by a spatially varying refractive index of air. Refractive index measurement. Homogeneous media. The refractive index of liquids or solids can be measured with refractometers. They typically measure some angle of refraction of the critical angle for total internal reflection. The first laboratory refractometers sold commercially were developed by Ernst Abbe in the late 19th century. The same principles are still used today. In this instrument, a thin layer of the liquid to be measured is placed between two prisms. Light is shone through the liquid at incidence angles all the way up to 90 degrees i.e., light rays parallel to the surface. The second prism should have an index of refraction higher than that of the liquid, so that light only enters the prism at angles smaller than the critical angle for total reflection. This angle can then be measured either by looking through a telescope, or with a digital photodetector placed in the focal plane of a lens. The refractive index N of the liquid can then be calculated from the maximum transmission angle theta as N equals Ng sin theta, where Ng is the refractive index of the prism. This type of devices are commonly used in chemical laboratories for identification of substances and for quality control. Handheld variants are used in agriculture by e.g., winemakers to determine sugar content in grape juice, and inline process refractometers are used in e.g., chemical and pharmaceutical industry for process control. In gemology, a different type of refractometer is used to measure index of refraction and birefringence of gemstones. The gem is placed on a high refractive index prism and illuminated from below. A high refractive index contact liquid is used to achieve optical contact between the gem and the prism. At small incidence angles, most of the light will be transmitted into the gem, but at high angles, total internal reflection will occur in the prism. The critical angle is normally measured by looking through a telescope. Refractive index variations. Unstained biological structures appear mostly transparent under bright field microscopy, as most cellular structures do not attenuate appreciable quantities of light. Nevertheless, the variation in the materials that constitutes these structures also corresponds to a variation in the refractive index. The following techniques convert such variation into measurable amplitude differences. To measure the spatial variation of refractive index in a sample, phase contrast imaging methods are used. These methods measure the variations in phase of the light wave exiting the sample. The phase is proportional to the optical path length the light ray has traversed, and thus gives a measure of the integral of the refractive index along the ray path. The phase cannot be measured directly at optical or higher frequencies, and therefore needs to be converted into intensity by interference with a reference beam. In the visual spectrum, this is done using Zernica phase contrast microscopy, differential interference contrast microscopy, or interferometry. Zernica phase contrast microscopy introduces a phase shift to the low spatial frequency components of the image with a phase-shifting annulus in the Fourier plane of the sample, so that high spatial frequency parts of the image can interfere with the low-frequency reference beam. In DIC, the illumination is split up into two beams that are given different polarizations, are phase-shifted differently, and are shifted transversely with slightly different amounts. After the specimen, the two parts are made to interfere, giving an image of the derivative of the optical path length in the direction of the difference in transverse shift. In interferometry, the illumination is split up into two beams by a partially reflective mirror. One of the beams is let through the sample before they are combined to interfere and give a direct image of the phase shifts. If the optical path length variations are more than a wavelength, the image will contain fringes. There exist several phase contrast X-ray imaging techniques to determine 2D or 3D spatial distribution of refractive index of samples in the X-ray regime. Applications. The refractive index is a very important property of the components of any optical instrument that uses refraction. It determines the focusing power of lenses, the dispersive power of prisms, and generally the path of light through the system. It is the increase in refractive index in the core that guides the light in an optical fiber, and the variations in refractive index that reduces the reflectivity of a surface treated with an anti-reflective coating. Since refractive index is a fundamental physical property of a substance, it is often used to identify a particular substance, confirm its purity, or measure its concentration. Refractive index is used to measure solids, liquids, and gases. Most commonly it is used to measure the concentration of a solute in an aqueous solution. It can also be used as a useful tool to differentiate between different types of gemstone, due to the unique chatoyance each individual stone displays. A refractometer is the instrument used to measure refractive index. For a solution of sugar, the refractive index can be used to determine the sugar content.